4.3 continues on with the multiplication rule, but it goes into complements and conditional probability a little bit more than we've seen before. So complements, the probability of at least one. So at least means one or more. So the complement means get no items of that type. So if we're saying that the event A is at least one, then the complement A with the bar, A complement, get no items of that type. So we can use the complement rule to find out the probability of at least one. You do 1 minus the probability of the complement. So example 1, a couple plans to have 3 children and want to know the probability of getting at least one girl. So we are going to say probability of at least one girl. And that can be found by doing this rule, 1 minus the complement. So at least one girl, then the complement would mean no girls. So 1 minus the probability of no girls. So whenever you have 3 children, how many events are there? Yeah, it's 8 because each time there's 2 chances, right? This is the first kid. This is the second kid. There's 2 chances. The third kid, there's another 2 chances. So 2 times 2 times 2 is 8. So that's your total. And then how many events would have no girls at all? What would that event look like? Yeah, there'd just be one. What would that event look like? Yeah, boy, boy, boy. That is the only event that gets no girls. If you needed to, if you weren't sure about this, you could list out every single event that could happen. So boy, 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 we have boy, girl, girl, boy, girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, and what's the last one I'm missing? Girl, 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 girl.
No, you have girl, girl, girl up there.
Oh, so what am I missing?
Girl, girl, boy.
Girl, girl, boy. I have that one twice.
Yeah.
So it should be
Boy,
boy, boy, girl. There we go. So obviously this way was better for me. Listing them out, I made some mistakes. So probability of no girls would just be that 1 out of 8. So it'd be 1 minus 1 out of 8, which would be 7/8. So that is 0.875. So it's pretty high probability. If you have 3 children, you want the probability of at least one girl. It's pretty high probability. Okay, let's look at the next one. You flip a coin twice and want to know the probability of getting at least one tail. So how could we use that rule of the at least one to find the probability of getting at least one tail? What would we subtract? Y'all can talk.
1 minus probability of no tails.
Yep. 1 minus probability of no tails. Let's think about how many outcomes there are whenever you flip a coin twice. Yep, there's 4 because the first coin, there are 2 outcomes. Second coin, there are 2 outcomes. So 4 total outcomes. And you want probability of no tails. So what is that event? Whenever you get no tails, what do you get instead? Heads, heads. So there's only 1 event out of the 4. So 1 minus 1/4. Just 3/4. 0.75. Okay, I was reading the book and they gave me some data. The probability of a hole in one is 1 in 12,000. Did you know that? It's a lot. It's crazy. But if we know that the golfer is a professional golfer, then the probability is 1 in 2,375.
Significantly lower.
Yeah. So I'm going to write that. Probability of a hole in one is 1 in 12,000. But if we know that the golfer's pro, then it changes the probability. So I can write this. This is conditional probability. We want probability of a hole in one given that it's a pro golfer. Then the new probability is 1 in 2,375. Much better odds if you're a pro golfer.
Yeah.
Still pretty slim, but a lot better odds. So this is called conditional probability. We're given additional information, and that additional information can change the probability. We don't know anything about these people that are doing the hole in one. But this one, we know that they're all pro golfers. So conditional probability, it's used when the probability is calculated with some additional knowledge. So I think we talked about this in 4.2, probability of B given A. So we're finding the probability of B knowing that A has already occurred. A confusion of the inverse. Incorrectly believe that probability B given A and probability A given B are the same, or to incorrectly use one value for the other. So inverse, do y'all remember that back in geometry? We talked about inverses, where you switch out your events A and B. So we cannot say, sometimes it's true, but we cannot say that these are true. You can't switch the order of those events. Probability of B given A is not the same as probability A given B. So this example is a pretty good one. Consider the probability that it's dark outside given that it is midnight. So probability of dark given midnight equals 1. Conveniently ignoring the Alaskan winter in such locations. But the probability that it's midnight given that it's dark outside, is almost 0. Therefore, probability of dark given midnight does not equal probability of midnight given dark. So I have to kind of break it down to make it a little bit more sense. So probability of dark given midnight means it's dark given it's midnight. So we know it's midnight. So is it going to be dark? Yeah. So that's 100% probability. That's certain. So that equals 1. But then if we switch it around, probability it's midnight given that it's dark. So we know it's dark. So what's the probability that it's midnight? Think about what time it gets dark. Let's say 7 o'clock, And it's dark from what time? 7 o'clock to about 6 o'clock, let's say. And so what's probability it's exactly 12 a.m. on the dot? It's like 1 out of how many hours is that? How many minutes is that? How many seconds?
11 hours.
Yeah.
So,
Well, it'd be 11 times the 60 because we're talking about midnight on the dot. So it's a much smaller probability than this certain one. What would that be? Let's say it's midnight between 12 and.
if you're going right on like the second, it's 39,600.
Oh, on the second,
Yeah.
it's what?
39,600.
Thousand.
But if you're going by just
The minute,
the minute, it's 660.
660. So we could say this or this, considering are we talking about on the dot, on the second, or with the minute? But you can obviously tell these are different. So you can't say the inverses are the exact same. Okay, so we're looking back at that table that we used during 4.2, the pre-employment drug screening with positive and negative results, and then we have our true positive, false negative, true negative. If 1 in 300 subjects is randomly selected, find the probability that the person tested positive, given that he or she actually used drugs. So let's do probability of positive, given that they used. Used. So we are only looking at the used side, right?
Mm-hmm.
So how many were positive on the used side? 119 out of how many total? But we're only looking at the used.
Oh.
122. So we already know that they used. So we know that all of these used, right? So that's the 122. So we're only looking at that. And then what's the probability that they're positive? It's 119 out of the 122. When we divide, we get 175 thousandths. Okay, so then the next one, if 1 in 300 subjects is randomly selected, find the probability that the person actually used, given that they tested positive. So probability they used, given that they are positive. So it's the inverse. So we're only looking at those that tested positive. So we're looking at these. How many of them used? 119. Out of how many total that were positive? 143. $832,000. Okay, so that is all of your notes. So you do have a My Math Lab assignment for 4.2 and 4.3. And make sure you're also working on your project.